Welcome everyone, and today we are happy to have Kurt Hinterbichler, and he will speak about unitarization in Kaluza Klein theory and the geometric bootstrap. So please start.
Okay, thank you. So thank you very much for this invitation. So I'll be talking about this unitarization in Kaluza Klein theory and this geometric bootstrap that results from it. So mostly I'll be talking about these first two papers here with my collaborator, James Bonifacio, who's now at Cambridge. So he's here as well in the audience today if there's any questions. And I'll also advertise this follow-up paper that he did, which goes beyond what I'm going to talk about today and gets new constraints on hyperbolic manifolds. Z bosons, if we just include the self-interactions of these bosons and don't include any Higgs or anything else, then we know that the amplitude, say the 4-particle tree-level amplitude for scattering longitudinal modes of these particles will grow at high energies like energy squared. So as you go to energies beyond about a TeV, in the case of the standard model, this amplitude starts to become larger than order 1, and you're violating perturbative unitarity. So you know that something new has to happen, either strong coupling or new particles or some new physics has to kick in. So this was the no-lose theorem for building the LHC. You know that if you go to these energies, something has to happen to restore unitarity to these amplitudes. So in the case of the standard model, we know what does that. We know that there's a Higgs mechanism. And in a weakly coupled Higgs mechanism, you add in a new particle. So in this case, the physical Higgs particle, which is now a new scalar. And when you add it in at tree level with its correct couplings, it cancels off this bad energy squared high energy behavior and makes it so that the energy Okay, so we can ask the same question about higher spin. So let's consider massive spin 2 scattering. So if I have some kind of generic massive spin 2 theory, like Nima and Georgi and Schwartz considered back in 2003, you write down the Einstein-Hilbert action plus some generic potential for the graviton. What you'll find is that the high energy scattering of the longitudinal modes of the massive spin 2 now grow with energy like e to the 10th. It's a very bad high energy behavior. There are special choices of this graviton potential that you can make, which soften that high energy behavior through various cancellations and make it go only like e to the 6th. So this goes by the name of DRGT massive gravity or ghost-free massive gravity. It turns out that this is the best you can do if you have a finite number of interactions for these, or rather if all you have is a massive spin 2 and no other particle, no matter what interactions you write down, as long as there's a finite number of derivatives, but still not, it can be any number of derivatives as long as it's a finite number, then there's no way to soften the behavior beyond this e to the 6th. So we have this paper here where we prove this. Okay, but then you can ask about, is there an analog of a gravitational Higgs mechanism? Is there a way to add new physical particles with spin less than 2 such that you cancel off, soften the high energy behavior and make it better than e to the 6th? So this would be like a true gravitational Higgs mechanism in the sense of making massive gravity better behaved at high energies by adding new lower spin particles. And we show in this paper that there's no way to do that with a finite number of lower spin particles. So with any finite number of lower spins with any couplings, there's no way to add them in to soften the behavior beyond better than e to the sixth. So this is some kind of boundary for massive spin 2 scattering. Okay, but we know there's exceptions to this if you allow for infinite numbers of particles. So for example, in string theory, we know that if you add an infinite number of massive higher spins in the right way, that you can make the tree level amplitude well behaved at high energies. But you can also do it without higher spins, just with spins less than or equal to 2 by considering Kaluza Klein theories. So say that we have a Kaluza Klein theory where we have some pure gravity theory in higher dimensions with some higher dimensional metric. We compactify that down to lower dimensional, like 4-dimensional space-time on some internal manifold, which we'll take to be some n-dimensional compact smooth manifold with internal metric little gamma here. So the pure gravity theory in higher dimensions, when you reduce it, it becomes a theory of an infinite number of massive spin 2 particles plus other things that are all self-interacting from the point of view of the lower dimensions. So if we consider amplitudes in this lower dimensional theory, we know that the higher dimensional theory is just pure general relativity. And we know that graviton amplitudes in general relativity only grow like energy squared. They behave much better than the massive gravity amplitudes. So we know that if we take the lower dimensional Kaluza Klein theory, if we keep all the Kaluza Klein modes, keep the entire tower, this should be just a rewriting of the higher dimensional gravity theory. And so the amplitudes should behave the same way. The amplitudes should behave like energy squared. That lower dimensional theory has massive spin 2 states in the spectrum. So if we look at the scattering where we have external massive spin 2s, there now has to be some cancellation if we include all of the various Kaluza Klein modes. That gets us beyond this energy to the 6th barrier that you had for just a single massive spin 2 and allows us to have amplitudes that only grow like energy squared. So we want to understand the mechanism for this cancellation. Okay, so we're going to be interested in just pure gravity in higher dimensions. And the higher dimensional Einstein's equations, the background has to satisfy the higher dimensional Einstein's equations for a graviton to propagate on it. So that tells you that the internal manifold has to be an Einstein manifold. So its Ricci curvature has to be proportional to the metric. And all the non-trivial constraints that we're going to derive ultimately depend on this condition. As we'll see, all the non-trivial juice that we get is going to come from this condition. So the spectrum of particles that we get in lower dimensions is determined by various Laplacians that we have on this internal manifold. So there's going to be 3 Laplacians of interest that we have to consider. So there's going to be the scalar Laplacian, which is just the ordinary Laplacian on scalars. There's the Hodge Laplacian on vectors, and then there's a Leshnerowitz Laplacian for symmetric traceless transverse tensors. So let's review what these various Laplacians and their spectra look like. So starting with the scalar Laplacian. So the scalar Laplacian has some set of eigenfunctions, which are just scalars that we'll label with this little a, and some set of eigenvalues that we'll label with lambda little a. So we know all these eigenvalues have to be greater than 0, and we'll treat the 0 mode separately. We'll choose these to be orthonormal in the standard inner product of just integrating over the internal manifold. And then they're complete. So I can write any scalar as a linear combination with some coefficient c of these scalar eigenfunctions. And then here's the 0 mode being treated separately. And V here is the volume of the internal space. So this makes it all everything normalized. There exists a special set of these scalars, a specific eigenvalue, such that they satisfy this equation here. These are known as the conformal scalars. And the conformal scalars exist only on round spheres, and they exist only for this one particular choice of this eigenvalue. There's a bound on the scalars So we're on an Einstein manifold here. So R is the constant curvature of the manifold. And this bound, known as the Lishnerowitz bound, says that all the non-zero eigenvalues have to be greater than this number. And this bound is saturated only by the conformal scalars. So the conformal scalars are the ones whose eigenvalue is precisely equal to R over n minus 1, and they exist only on the spheres. Okay, let's look at the vector Laplacian now. So this is the ordinary Hodge Laplacian on one forms. So the vectors here are all going to be transverse, and the eigenfunctions are denoted by y. So m is the vector index, and I is labeling the different eigenfunctions. So they're orthonormal in the inner product, and there's some completeness relation that they satisfy, which follows from Hodge decomposition. So the completeness relation says that any vector can be written as a sum over these transverse eigenfunctions plus longitudinal vectors, which are just derivatives of the scalar eigenfunctions. There's a special set of vectors which are the killing vectors, which satisfy the killing equation, and these occur for a particular eigenvalue. And there's a bound which says that all the non-trivial eigenvalues have to be larger than this number, and this bound is saturated only for the killing vectors. So in particular, if the curvature is negative, you don't have the killing vectors. Okay, then finally, we have the tensor Laplacian. So this is going to be the Lishnerowitz Laplacian that's acting on transverse traceless tensors. So squiggly I is going to be labeling the various eigenfunctions, lambda squiggly I the eigenvalues. There's some orthogonality condition that these satisfy, and there's a completeness relation, which says that any two-index tensor can be written as a sum of these transverse traceless tensors plus longitudinal stuff, which involves the vector eigenfunctions as well as the scalar eigenfunctions, and then trace stuff, which only involves the scalar eigenfunctions. And there's a special eigenvalue here as well, which are what you might call the zero modes. This particular eigenvalue, these correspond to the moduli space of Einstein structures. So these eigenfunctions can be thought of as infinitesimal deformations of the metric that preserve the Einstein condition. In general, there's no known lower bound on the Lishnerowitz Laplacian. It's possible that there can be some negative eigenvalues. There has to be a finite number, so the spectrum does have to be bounded from below, but there's no generic lower bound in terms of the curvature that's known.
Sorry, what is the origin of these bounds? Is it a requirement of what?
So these are just mathematical theorems about the eigenfunction. So for the Lishnerowitz bound, this was just some theorem that's.
So you take like any compact manifold, then Laplacian in it, and then the statement is that. Mm-hmm.
Yeah.
Okay, thank you.
Yeah. Okay, so now we have to find the spectrum of the Kaluza Klein theory. We need to expand the metric. So we break up the metric into its four-dimensional part, its extra-dimensional part, and then the mixed part. So in lower dimension, we have tensors, vectors, and scalars. So we have to expand these now over the eigenfunctions. So here we expand the lower dimensional tensors over the internal scalar eigenfunctions. So we get a tower of lower dimensional tensors here and a zero mode tensor. Then the vectors we expand using the internal vector completeness relation. So we get four-dimensional vectors, and then we get two sets of four-dimensional vectors, and then we get a bunch of lower dimensional scalars from expanding the tensor eigenfunctions. So not all of these things are physical because there's gauge symmetries we have to worry about. So the things that are in blue here end up being the physical fields, and the things that are in red end up being longitudinal modes like Stuckelberg fields that get eaten when you fix the gauge symmetry. So this first tower of tensors here, these are massive tensors, so they have to eat longitudinal modes consisting of a vector and a scalar. And then this tower here becomes massive scalars, so it has to eat a longitudinal mode here. So at the end of the day, the true physical modes that you get are the following. So we get a massless graviton from the zero mode of the scalar Laplacian. We get a tower of massive gravitons whose masses are determined by the non-zero eigenvalues of the scalar Laplacian. We get a tower of vectors with masses given by the eigenvalues of the Hodge Laplacian. And these vectors are massless only if the eigenvalue is correct to be a killing vector. So we get massless vector for each killing vector. And then we get two different towers of scalars. We get a tower of scalars coming from basically the trace parts expanding in the scalar eigenfunctions. So these masses depend on the scalar eigenfunctions, and you get a zero mode precisely for what's basically the volume modulus of the internal space. So there's always one massless scalar for the volume modulus. And then you get another tower of scalars corresponding to the eigenvalues of the Lichnerowitz Laplacian. And these scalars are massless only if the eigenvalue is such that it corresponds to the Einstein structure moduli. So these are like the shape moduli. So these happen only if you have zero modes for the Lichnerowitz Laplacian. Okay, so here's the case now if we want to do amplitude stuff, which we're interested in. So we want to have an S matrix in lower dimensions. So we want to compactify to a flat lower dimensional space. So that means the internal space should be some Ricci flat internal manifold. So we'll when we're talking about amplitudes, we'll have this Ricci flatness condition, but then eventually when we get to the bootstrap, we'll relax this and consider curved internal manifolds. So the closed Ricci flat manifolds are relatively rare. The only known examples are flat tori, the Calabi-Yau manifolds, and then a few of these special holonomy manifolds, G2 and spin 7. All of these known examples have special holonomy, and there's a recent theorem that says that if you have special holonomy, that the spectrum of the Lichnerowitz Laplacian is always positive. So these have no negative eigenvalues for that particular tower of scalar, but it's not proven in general that all Ricci flat manifolds have a positive Lichnerowitz spectrum. It's still possible that there are some undiscovered Ricci flat manifolds that have a negative spectrum. So here's what the spectrum looks like in this flat case. So we have these two different spin 2 towers, the one coming from the scalar Laplacian always has one massless mode and then a tower of masses corresponding to the scalar Laplacian eigenvalues. And then there's the tower of scalars from the Lichnerowitz operator. And these can be massless only if you have moduli. And it's possible there could be tachyons if there's some undiscovered Ricci flat manifold that doesn't satisfy this positivity condition, but all the known examples, there are no tachyons. And then there's this tower of massive spin 1s, which comes from the vector Laplacian, which are massless only if you have a killing vector. And then there's this tower of spin 2s, which comes again from the scalar Laplacian. And there's always one massless one, the zero mode graviton, and then a tower of massive spin 2s. Okay, so that's the spectrum. So if we want to consider scattering of these massive spin 2s, so we have some 4-point amplitude with external massive spin 2s, we now have to include all of these towers in the exchanges. So we have to include here the massive spin 2s in the exchange, as well as the massless and the vectors and both towers of scalars, as well as the contact amplitude among the massive spin 2 that arises from the dimensional reduction. Okay, so what are all the interactions we need to compute this? We need all the various cubic interactions that appear in these exchange diagrams. So we'll need the cubic interaction that has 3 massive spin 2s that are all interacting. So that has a cubic coupling, which is proportional to the triple overlap integral of 3 of these scalar eigenfunctions. So that's what's denoted by G here. And we'll need the cubic coupling between two massive modes and the massless graviton. So this is fixed basically by just minimal coupling. So there's no free cubic coupling here. We'll need the interactions between the massive spin 2 and the massive vector tower. That cubic coupling is given by a triple overlap integral that involves two of the scalar Laplacians corresponding to these massive spin 2s, as well as one of the vector Laplacians corresponding to the spin 1, as well as an insertion of the derivative. And then we'll need the coupling between the massive spin 2 tower and the massive spin 0 tower coming from the scalar Laplacian. So that's again a triple overlap between scalar eigenvalues. And lastly, the cubic interactions between massive spin 2 towers and the Lichnerowitz tower of scalars, which involves a triple overlap between two scalar eigenfunctions, a Lichnerowitz eigenfunction, and two insertions of derivatives. And you can check that all these cubic vertices have the correct symmetry properties among interchanges of particles and so on. Okay. And then finally, we'll need the quartic interaction, which involves a quadruple overlap integral between scalar eigenfunctions. Okay, so now we have all the ingredients. We can just brute force compute this amplitude and expand it at high energies to see how it behaves at high energies. So what you find is the leading behavior would presumably go like e to the 10th. That's the generic high energy behavior of a massive spin 2. And then there's all these subleading parts going down, and these coefficients alpha 10, alpha 8, alpha 6 have just a bunch of kinematical factors. So like the scattering angle theta and various eigenvalues, and then various cubic couplings. So if this amplitude really behaves like energy squared, then it means that these first four e to the 10th down to e to the 4th, these leading behaviors all have to cancel. These alphas must independently vanish. Okay, so let's look at this leading e to the 10th alpha. So the thing that has to be true for this to vanish is the following sum rule. The quartic overlap integral has to be related to the triple overlap integrals in this way. So this is now just some mathematical property of eigenfunctions that has to hold on any Einstein manifold. This is a purely mathematical statement that just has to be true in order for this amplitude to cancel. So we can see where does this statement come from. So if I have a product of eigenfunctions like this here, that product, if I'm talking about the scalar eigenfunctions, that product is again just a scalar. And because of completeness of the eigenfunctions, I can expand that scalar in terms of eigenfunctions again. So any product of two scalar eigenfunctions can be expanded in this way. And the coefficients of the expansion are just the triple overlap integrals, as you can see by just contracting with another psi here and taking the integral of both sides. So this is kind of like a operator product expansion, if you like, where I can take any two things within a overlap integral and expand it into a sum of one function. So I can reduce any multi-overlap integral like this to just a sum of triple overlap integrals by repeatedly using this completeness relation. But there's going to be multiple ways of doing this. So if I look at the quadruple overlap integral, there's four different ways in which I can use this completeness relation given by the four different ways of contracting two pairs of these eigenfunctions. So this is going to give some kind of associativity condition or a crossing relation on the four-particle overlap integral. And that's reduces to precisely these equations up here that have to be satisfied for the e to the 10th contribution for the amplitude to vanish. Okay, so a similar thing then has to go at the subleading order. So if we look at the e to the 8th sum rule, that has to be satisfied. This is the condition that has to be true. So this, again, has to be some property that's just true of internal manifolds, Einstein manifolds. And now this can be derived from a crossing relation where we have a quadruple overlap with two insertions of derivatives in this way. So if you work out this with all the derivatives and everything, it reproduces this up here. So this now has some non-trivial consequence. So if we look at this term, the second term here, this always has to be positive because the eigenvalues are always positive. So it means that this, and g squared is always positive, so this coefficient here has to be negative for some choice of A. So there has to be some massive mode for which you get a negative value here, which means that whatever particle I'm scattering, there has to exist some other particle that I'm exchanging whose mass is larger by this amount here, so that this thing here can be negative. So if I scatter some external massive particle, we know that there has to exist a more massive spin 2 in the spectrum. And now I can repeat that, and I can take that more massive one and put that in the external legs, and then that there has to be another one more massive still, and so on. So this proves that there has to be an infinite number of massive modes in the tower. Unitarity, or the canceling of this high energy behavior, requires that there be an infinite tower of states. Or if you like, this is another proof that the number of eigenfunctions has to be infinite. And furthermore, they all have to couple non-trivially. They're the infinite tower. You can't have the situation where some finite number of things couple and then they decouple, because this coupling G here has to be non-zero for this cancellation to occur. Okay, so now we can go down. If we look at the e to the sixth sum rule, that comes from a crossing relation now where we insert 4 derivatives. And then if we look at the e to the fourth sum rule, this now comes from a crossing relation where we insert 6 derivatives. So let's look at this. This is some non-trivial relation that now has to be true that involves the Lichnerowitz eigenvalues as well as the couplings. So if we look at this condition, we can make a similar kind of argument. So this second term here, everything is positive under the assumption that the Lichnerowitz eigenvalues are all positive. So if we assume that these Lichnerowitz eigenvalues are positive, which again we know is true for all the known examples, then this second term has to be positive. So this first term here has to vanish. So, or it has to be negative so that this whole thing can vanish. So these, this coupling here is always squared. The eigenfunctions here are always squared. So this polynomial that appears, which depends on ratios of eigenvalues, always has to have some negative value. And that shows, it gives you an inequality.
Yeah. May I ask a question? What about the case of n equals 1? When the second term disappears?
Yeah, so that case is kind of trivial because that's just a circle. So we can just treat that case specially, but it also satisfies the statement I'm about to say.
Mm-hmm. Mm-hmm. Okay.
So this shows now that for any closed Ricci flat manifold, such that this positivity condition is true, that there's a bound on the ratio of sequential eigenvalues, that the k plus 1th eigenvalue can never be more than 4 times greater than the kth eigenvalue. So what this does is bound the gaps that you can have between Kaluza Klein excitations in the Kaluza Klein spectrum. So you can't have a situation where you have a Kaluza Klein theory where you have an enormous gap between some of the modes. And this applies, this is just a statement about eigenfunctions of the scalar Laplacian, so it also applies to smooth Calabi-Yau compactifications in string theory or M theory, or anytime you're compactifying on a Ricci flat internal manifold satisfying this assumption. So this kind of rules out, if you're talking about theories of effective field theories that have massive spin 2s, one way you would like to derive such an effective field theory, if you want there to be a finite number of massive spin 2s, is to have a situation where there's a parametrically large gap in the eigenspectrum. Because if you have such a situation, then you can integrate out everything above the gap, and then you'd be left with some finite number of modes below the gap, which would give you a well-defined effective field theory. But this tells you that you can't arrange such a situation within the Kaluza Klein theory. So you can't construct an effective field theory of massive high spins in this way. Okay, so we also know that this bound is optimal. There are certain tori in every dimension that saturate this bound. So there's no better bound than this. And we checked, it's non-trivial. So for example, the quintic-Calabi-Yau manifold, if you look at its eigenvalues, you can't compute these exactly, but these people have numerically computed them and have given some spectrum. So this is the spectrum in units where the volume is 1, and it does satisfy this condition. This condition, it's essential that we have the Einstein condition for this to be true. So there's this funny theorem that says that if I don't have the Einstein condition, so if I just have some generic closed Riemannian manifold, if you give me any non-decreasing sequence of positive numbers, I can find a metric on that manifold such that that sequence is the first k non-zero eigenvalues of this metric. So you can get any spectrum you like, essentially, on a generic Riemannian manifold. But with the Einstein condition, you can't. So if we were doing Yang-Mills theory dimensional reduction, you could get gaps in the spectrum. There'd be no problem. But with gravity, you can't. Okay, so there's a kind of analogy between all this and what CFT people do. So we can think of, if we think of CFTs, we like to have primary operators. And that you can think of as analogous to these eigenfunctions that we're talking about on Einstein manifolds. And you can think of eigenvalues as like the scaling dimensions of these operators. We have these multiple overlap integrals. These are the objects of interest that enter into all our amplitudes and physical quantities. That's analogous to correlators in a CFT. We have derivatives that we can insert into these overlap integrals, and that's analogous to in CFT having descendant operators. We have this completeness relation among the eigenfunctions, which you can think of as analogous to the operator product expansion in a conformal field theory. We have these various sum rules that have to be satisfied among the multiple overlap integrals when you use completeness to reduce them. This is like the crossing relations in conformal field theory that you get from applying the OPE in various channels. We have these various bounds on the eigenfunctions that are analogous to unitarity bounds in CFT. And we have what you might call geometric data for the manifold. So the set of all eigenvalues along with these triple overlap integrals is enough to tell you what all the multiple overlaps integrals are because of this completeness relation. And same with CFTs. So in CFTs, you talk about the CFT data of the scaling dimensions of your primary operators, as well as the OPE coefficients, which are the 3-point functions, and then all the higher point functions are determined in terms of that. So on the CFT side, people like to say that a CFT is defined by this CFT data. In other words, any set of this data that satisfies the crossing relations kind of uniquely defines a CFT for you. What we'd like to know is if the same is true on the geometry side. So is it true that a Einstein manifold is uniquely determined by its geometry data? If I give you this lambda and the triple overlaps, does that uniquely determine a manifold? And we know, for example, that the eigenvalues themselves are not enough because there are isospectral manifolds, things that are geometrically different that have the same spectrum. That's the famous "you can't hear the shape of a drum." But it may be if you include the triple overlaps, maybe that's enough to hear the shape of a drum. So we don't know if this is true. It would be interesting if there were some kind of non-geometric geometry data. If there was some set of these lambdas and g's that satisfies all the crossing relations but did not correspond to any geometry, that would be an interesting thing to have, because that would give you a ostensibly consistent Kaluza Klein reduction that doesn't actually come from a geometric manifold.
So I may ask a question about this analogy.
Yeah.
So is there any analog of conformal block on the left-hand side column? Because conformal block in CFT is model independent quantity affected by symmetry arguments.
Yeah, but it's also not an independent thing because it's given as just sums over the triple over. I mean, it's basically, you can write it as sums over OPE coefficients and stuff, okay? And various. I don't think it's independent data that you need for a CFT.
But anyway, you can decompose and correlate in conformal blocks, extracting these CFT data in front of these functions.
Yeah, so you could probably say a similar thing here. You can decompose any 4-point function into sums of g's, which you could call blocks or something like that. Okay, so the CFT people have their CFT bootstrap. So we want to do a similar thing. So these crossing relations seem to give us non-trivial relations. So this constraint that we found on the eigenvalues, this is something that followed from that crossing relations. And as far as we know, this was not known to mathematicians at all before. They hadn't looked at these triple overlaps or crossing conditions. So we want to try to get more out of that. We want to, like the CFT bootstrap people, try to exploit these crossing conditions more in order to constrain the CFT data. So now we're going to go back to the case of a general Einstein manifold. So forgetting about the amplitudes and the Kaluza Klein reduction. So we're not going to necessarily have a Ricci flat internal space. We're going to allow for curvature in the internal space. And we're just going to take these crossing conditions and evaluate them and try to exploit them in a numerical bootstrap condition. So here are the 3 different crossing conditions that we were able to have. So you have, well, there was the kind of trivial one that had no derivatives. There's ones with 2 derivatives, 4 derivatives, 6 derivatives. And then it turns out that for Einstein manifolds, this is as far as you can go. You could try to insert 8 derivatives, but then you'd find that there's no way to manipulate those derivatives in such a way that you get rid of all the curvature terms that can't be reduced just with the Einstein condition. So there's kind of a limit to how many crossings we can write down. If we impose stronger conditions, if we impose maximal symmetry on the internal space, this is what James did in his latest paper, then you can continue this and add more and more derivatives and get more and more non-trivial constraints. But for now, we have to stop here. So these give you these crossing relations that we wrote down before. You can package these all together into some giant set of things here with these f's, which are various just vector quantities that just package together all the relations that I showed before. And now you can set this up as a bootstrap problem. So what we do is to postulate some candidate geometric data, so some collection of eigenvalues and triple overlap integrals. And then you search for some set of constant vectors such that when you dot it into these conditions that we know have to be true, can never be satisfied. And if we find such a constant vector, then we've ruled out this candidate geometric data. So it's just like the conformal bootstrap where you have some, you get some plot and you test different candidate geometric data and then you rule them out and you get some kind of exclusion plot. So the problem here is formulated in exactly the same way and it can be solved using the same open source semi-definite program solver that the bootstrap people use, and in some simpler cases, even Mathematica can do it. So this is basically James is the one who figured out how to set this up and made all the plots that I'm about to show you. Okay, so I'm going to show you just a sampling of some kinds of exclusion plots that we're able to get from these numeric bootstrap procedure. Okay, so here is a plot where we're showing an exclusion plot of the ratio of the two lowest lying scalar eigenvalues. So that's lambda A2 over lambda A1 here, as a function of the smallest Lichnerowitz eigenvalue. So it's basically like the second scalar eigenvalue versus Lichnerowitz eigenvalue in units of the lowest eigenvalue. So the bound that we found earlier when the curvature is equal to 0 is this gap of 4 that can't be exceeded. But now we're going to get stronger bounds using this full numericals procedure. So here the various lines are just the dimension of the internal manifold. So the blue line here is for two-dimensional internal manifolds, and then three-dimensional and so on. And these are upper bounds. So any true manifold that you have has to lie below these curves. So these dots here lying below the curves are some examples where we can compute explicitly the spectrum. So basically the only manifolds where you can explicitly compute the spectrum are the spheres, projective space. So here RP is real projective space, CP is complex projective space, and then tori. So all the examples we can compute exactly fall below these bounds, and the bound is stronger than this one we had before when the Lichnerowitz eigenvalue is non-trivial. We also get like a kink here, similar to what the conformal field theory people find. We don't know if this bound is optimal. We don't know if there's non-trivial manifolds living at this kink. Here's same thing, but now under an additional assumption. So an additional assumption that there's a Z2 symmetry under which the lowest eigenvalue is odd. So spheres, for example, satisfy this. So here we get even a slightly different bound. And here we're getting close to optimal, at least in some region, because the spheres lie exactly on this line that we find. Here's another kind of exclusion plot. So here we're looking at the two lowest eigenvalues, lambda 2 versus lambda 1 in units of the background curvature. So now we're talking about a background space which is positively curved. And we've shown here just 4 dimensions for illustrative purposes. And there's a few assumptions that we had to impose to get this this plot. And here there's actually a non-trivial kink where the sphere lives, where S4 lives. Here's the Lichnerowitz bound, which was saturated only for these conformal scalars, which live on the sphere. And then here is complex, two complex dimensional projective space. And there's another kink here, but again, we don't know if there's any non-trivial manifold that lives there. So we'd like to say something like, like in CFTs, when they're searching for CFTs, you have weakly coupled CFTs, which are exactly solvable, where you know the exact spectrum, and those should of course be allowed. But then there's the strongly coupled CFTs, which appear as generally as various kinks in these exclusion plots, things like the Ising model. So the sphere you might call as something like a weakly coupled manifold, because it's exactly solvable. You can find all the eigenfunctions and eigenvalues explicitly, but maybe there's some kind of non-trivial strongly coupled manifold, if you like, that lives at these kinks. We don't know. Okay, here's another plot. So this one's a bit busy. So again, we're assuming some curvature which is greater than 0, and we're going to assume this bound that's there's no negative eigenvalues for the Lichnerowitz Laplacian. So here's now the ratio of the third eigenvalue to the first eigenvalue. And these dotted lines are what you get, are upper bounds that you get generically in various dimensions. These solid lines are better bounds that you get if you impose, again, this kind of symmetry on the eigenfunctions. And then this weird purple region is the space of tori. So if you look at just all kinds of two-dimensional tori and the whole moduli space of them, this is the region that it fills out, and so it fills out some complicated region, but always below the bounds that we find. Here's another non-trivial point, the Fermat quintet Calabi-Yau. Okay, so those were all bounds on eigenvalues. We can also get bounds on these triple overlap integrals on the cubic couplings. So here is some upper bounds on the lightest massive spin 2 self-coupling. So the cubic coupling where all of the external particles are just the lightest massive spin 2 in the Kaluza Klein spectrum, again under certain positivity assumptions. So here we're plotting the various dimension, and then the blue dot here is the numerical bound that we find. And then these dots below are all specific examples of manifolds that we can compute exactly, and they all fall below the bounds as they must. Here's another set of bounds on cubic couplings. So here we're looking again at the self-coupling of the lightest massive spin 2 particle. That's the y-axis here, and then the x-axis is the ratio of the size of the second eigenvalue to the first eigenvalue, that ratio. So this ratio is the one that can't exceed 4. So these bounds in various dimensions, you see that as you try to make that ratio maximized, as you try to pull the eigenvalues as far apart as you can, the coupling goes to 0. So as you try to make the this mode get as far apart as possible, it basically tries to, it decouples. Okay, here's the same kind of plot, but now where we're looking at cubic couplings between the first Kaluza Klein, the first massive Kaluza Klein mode and the second Kaluza Klein mode. So same kind of thing, as you go try to optimize this gap in the spectrum, the coupling goes lower, but not exactly to 0 in this case. Here's another similar plot, just under stronger assumptions, some Z2 symmetry. So here we find there are spheres that kind of optimize these bounds. Okay, so these were all in the case of Einstein manifolds. So in this latest paper that James put out, he generalizes this to hyperbolic manifolds. So with closed hyperbolic manifolds, you have basically, they're locally maximally symmetric. So you can write down more of these crossing relations that involve more and more insertions of derivatives, and you can have tensor operators or tensor fields on the space which have arbitrary rank. You can have spin 3, spin 4, and so on tensors, and all the space of tensors is all nicely orthogonal and everything, and you can generalize these bounds much further. So here's a plot I took from his paper where he's looking at genus G Riemann surfaces and plotting exclusion plots for the second to first eigenfunctions. So in the case of Riemann surfaces, they're much more well studied. There are various mathematical theorems that put bounds on these. So these various boundary regions that are labeled here are the results of various mathematical theorems that bound the eigenfunctions. But then the bootstrap bound gives you another bound that closes this region, and it gets stronger as you go up in genus. Okay, so there's a bunch of other plots that are in our paper and in James's paper that there's much more other things that we can do. This was just a sampling of them, and there's much more that you could do that we haven't done yet. We certainly haven't exhausted the information that's in all these crossing relations, but I'll summarize here. So we found new non-trivial constraints on the possible spectra and triple overlap integrals of Einstein manifolds. So as far as we know, these constraints are not known to the mathematicians, and the only reason we found them was because of these physics considerations about high energy scattering and unitarity and so on. So they all come ultimately from these crossing relations on the multiple overlap integrals. They ensure the correct that this is the mechanism by which the Kaluza Klein theories give you better high energy behavior than just generic massive effective field theories. What we'd like to know is how far this can go, whether there are non-trivial manifolds that you could isolate that maybe live at the kinks of these bootstrap bounds, or even better, if you could isolate some non-trivial manifold by these bootstrap bounds. So in none of the constraints that we did were we able to actually isolate like an island the way that the conformal bootstrap people do. So the bootstrap people, when they first studied the Ising model, they saw it as some kink in this exclusion plot. But as they studied mixed correlators and other objects, they were able to isolate that into an island and make the island so small that you can actually compute critical dimensions very accurately from it. So we'd like to know if a similar thing could be done here. Could you actually compute low-lying eigenvalues by isolating an island in a similar kind of way? So this would be analogous. You can think of the way that these people computed eigenfunctions of the Calabi-Yau manifolds. That was kind of like a Monte Carlo analog of the Monte Carlo method of doing the Ising model, where you have to actually pick a model and then compute compute numerically a metric and find the eigenvalues and so on, and then it gives you the values for that model. What we'd like is more of this true bootstrap, where you don't commit to a model, but you bound it and isolate it just from constraints. And then mathematically, we'd like to know, is a manifold uniquely determined by this geometric data? Or are there true non-geometric Kaluza Klein compactifications that you consider? Are there data that satisfy all these crossing relations that do not come from any manifold, which would give a true non-geometric compactification? Okay, so I'll stop there. Thank you very much.
Thank you. Are there any questions?
I have a question. So if you just given some infinite set of these Kaluza Klein modes, and you don't really know where they came from, you need a prescription of how you sum over them. So once you have high dimensional theory, which in the UV limit has Lorentz symmetry of 10 dimensions, so that imposes certain conditions on how you should organize these modes so that they actually look like they came from 10-dimensional theory. Yeah, so there is a very special prescription which is consistent with this.
Well, I would say that that prescription is the condition that the high energy behavior scales like energy squared.
Okay, yeah, indeed, yes. So so that raises a question that you may discover some very special theories and you don't know what geometry is, but still somehow there is a hidden assumption that there is some high dimensional theory. Maybe it should have some Lorentz symmetry or something, some extra global symmetry, which is restored at high energies.
Yeah, I don't know, because the only high energy, like if you're the only thing that you want this to look like a flat space theory at high energies, so that's basically the condition that the energy goes like e to the square, and then that follows from these completeness conditions. So I would say these completeness conditions are the conditions you want for a generic tower to come together into a Kaluza Klein. Like
you're saying they are enough. But this is a tree level. Well,
yes, that's right.
Loops are a different story. Yeah,
that's a different story. That's right. But yeah, you could hope that the loops, that it's the same conditions, because ultimately when you're doing loops, you're still reducing and getting these, it's ultimately these same triple, quadruple overlaps and so on that's entering into the loops. So if I do that for Kaluza Klein theory,
the loops you'll have UV story theory.
You have the UV story, but whatever that story is should be the same as in the flat case. So if it works in flat space, these same conditions should ensure that it works in the Kaluza Klein case.
Okay.
May I ask you a question concerning determination of a manifold by geometric data? Have you some explicit examples when you can distinguish between isospectral manifolds by means of your triple overlaps?
Yeah, so I think in the case of tori,
Yeah, there are some high-dimensional tori isospectral.
Exactly. Yeah, so those are cases where, if I'm not mistaken, they're isospectral, but the triple overlaps are different.
Thank you.
Okay, Maxim.
Okay.
Thanks. This data of Riemannian manifold, which gives you this triple and high order overlapping integrals, is there any algebraic structure which comprise all these objects?
Yeah, not that I know of.
Because some equations look like sort of associativity and probably higher order analogs or some kind of weak.
Yeah.
Probably
yeah,
it was studied. I just don't know.
Yeah, so I'm not sure. So you could think of these triple overlaps as some kind of structure constant for an algebra, and the crossing relation would be some kind of Jacobi identity. So I don't know. You'd call that an algebra, but it's some kind of structure.
Other questions?
I'd like to ask a question, please. I missed the point about two towers of scalars when you discussing the spectrum of Laplacians in the first part. So I would expect that there should be three towers, each tower coming from spin 0, spin 1, and spin 2. Is it correct?
So here's the decomposition of the metric. So there's 4 different scalars that appear in the decomposition of the metric. So there's one that appears from decomposing the trace. There's the longitudinal mode of the spin 2, and there's the longitudinal modes of the vectors. And 2 of these get eaten as Goldstone modes for the massive spin 2 and for the massive spin 1.
So you mean as a result of fixed and shift symmetries in the final Lagrangian?
Yeah, because you have to fix the higher dimensional diffeomorphism symmetry down to lower dimensional diffeomorphism. So that eats the 2 of these scalars, and then 2 are left as physical.
So the conclusion is that originally we have more towers in this decomposition, but eventually when you fix Tuckelberg-like symmetries, we are left with just 2 towers, which is your picture, right?
Right.
Okay. So good. And one more question, please, about this bootstrap analogy. And so, if I understood correctly, this bootstrap analogy works for high-dimensional CFTs. But if you consider 2-dimensional CFT, we know that bootstrap can be solved for a particular class of models, minimal models.
Yeah.
The spectrum is finite dimensional. Is there any analogy on the gravitational side?
And not with the, so when you say that the spectrum is finite dimensional, that's when you're considering like Virasoro primaries, but in terms of the actual conformal primaries, it's still infinite.
Conformal family is infinite, of course, but just finitely many primary operators, which would correspond to finitely many eigenfunctions.
Yeah, but there's no, I mean, we know there's no manifolds that have a finite number of correlators, which I'd say, or a finite number of eigenfunctions, which I'd say is exactly analogous to the CFT case if you're thinking in terms of conformal primaries and not full Virasoro primaries. But the question of whether there's exactly solvable ones is interesting. Yeah, because that, you can think of these spheres or tori in some sense as like that. They're exactly solvable. You can write down the spectrum exactly and everything. I want to think of those as analogous to free CFTs, but whether there's non-trivial things that are not just spheres that are exactly solvable, as far as I know, there's not. There's no manifolds where you can get a closed form for the spectrum other than spheres and tori and projective spaces.
Okay, and a final question about symmetries. Considering CFT, we know that there is kind of global symmetry or local symmetry in high dimensions. It's OD, 2. In 2 dimensions, it's Virasoro symmetry. Can we say something about symmetry? Or
yeah, so if you have killing vectors on your internal manifold, that would be an analog of having global symmetries in a CFT. So all of the eigenvalue, all the eigenspectra, all the eigenfunctions would organize into representations of this symmetry. The multiple overlaps would all respect selection rules for this symmetry and so on. So that's similar to the global symmetry in a CFT.
Is it possible to identify the symmetry on the gravity side?
Well, so it would be you'd identify it in it would be just a global, geometric rotation of the internal space on the gravity side.
So it's just isometry of your manifold.
Yeah, isometry of the internal manifold. And then from the lower dimensional point of view, that's a global symmetry acting on the Kaluza Klein tower.
Okay, I see. Thanks.
Yeah.
Is it true that all these manifolds are even dimensional? Those which are compact and Ricci flat? There are no odd dimensional cases.
Well, other than the tori, I think that's true. Yeah.
Okay.
Well, so hold on. I thought that isn't the G7. Is G7, how many dimensions is that? Because people
should be
they compactify.
Yeah.
G2 is 7 dimensions, I think.
Yeah, G2 is 7 dimensions.
Oh, G2 is 7.
Yeah.
Okay. 7. Okay. All right.
Okay, can you use the experience gained from this to make the amplitude behavior even softer?
I don't think so, because that constraint was, if you could, then there would be a gravity theory that has better behavior than general relativity. So yeah, if you start with maybe string theory in the higher dimensions, that's even softer than general relativity. Yeah, indeed, there'd have to be some cancellation among now the massive string towers in higher dimensions that would translate to something in lower dimensions. So yeah, that.
So you need spans higher than 2 for this.
Yeah, that's right, because that's the only known way to make the gravity amplitude softer.
Okay, so are there any more questions? Okay, if no, thank you very much.
Hey, thank you.
Thank you.
May I ask you a last question, please?
Yeah.
So can we apply this machinery to 3-dimensional gravity?
Sorry, can you repeat that?
Can we apply this machinery to 3-dimensional gravity?
To lower dimensional gravity?
That's right.
Yeah, I think so. Nothing I said depended on dimension. I guess the only thing is that in lower dimensional gravity, some of these Kaluza Klein modes are not physical, so you can't scatter them anymore. Like if you go down to 3 dimension, there's no massless graviton, but there'd still be a massive graviton you could scatter. So you just have to look at different external states, but it should go through the same way.
And even in 2 dimensions?
Yeah, in 2 dimensions, there's nothing but scalars in 2 dimensions, but there are still massive scalars. So presumably if you'd scatter those, you'd see the kind of high energy behavior, and you could study that.
Okay. Thank you.
Okay, thank you once again, and to everyone for coming.
All right, thank you.